Okay, welcome back everybody. This is the 2014 Reversing Lecture Part 2. Now, we left off at the exercise where we figure out the stack frame for the source code right here. So, we're moving on to bigger and better things now, and starting off is recognizing patterns. So, everything we've done so far is this black background, white text, block of text, and it is not very exciting to look at. In fact, this is a short for loop from 0 to 10, and this program is not easy to recognize right off the bat. So, I mean, you can see it does a jump, it does a comparison, does another jump, executes some stuff, and does another comparison and a jump again. It's sort of convoluted to look at. Now, to compare that, on the right-hand side here, we have IDA. IDA is fantastic, and this is that exact same program shown in IDA's graphical format. Now, IDA breaks up blocks into basic blocks. So the code in any particular block you're going to take unconditionally. If you were to enter this program, wow. Okay, now if you were to enter this main block right here, these functions would be executed unconditionally. There's no way to get around it. However, if you were to enter this block right here, you could, depending on the comparison, you could take one branch or the other. So all the instructions in one basic block you're guaranteed to take regardless. And the reason that this block is split before this location is because another block jumps into that location. So that's how the basic blocks are broken up. But this is much easier, much cleaner to recognize. You sort of at a glance see, oh, well, some variable is being compared to 9. If it's less than or equal to, we're taking this branch and executing a loop. Otherwise, we're returning. So that's much easier to recognize right off the bat than this block over here. And also this dark blue line represents a loop in IDA. So even from a high-level view like this, without being able to see a single instruction, you can tell at a glance what this program is trying to do. So this common stair-step structure that you see over here, this is usually the result of a bunch of library calls or comparisons and then a failure case. So some function is being executed in here, the result is being checked, and on the failure case you're exiting. And then the same thing happens here, the same thing happens here. And this is really common on something like setting up a socket, where maybe you call some operation and then you check the result, and then you bind, and then you connect, and after each one of these cases, you might fail, and so you might want to exit. So, and here in fact is that graph zoomed in, and you can see, and then this one does happen to be a socket operation, but it could be anything. So you can see set sock option is being called, the return value, which is in EAX, is being compared to FFFFFFF, which that with 2's complement is -1. The same thing goes on, bind is being checked, listen is being checked, and so on and so forth. So IDA rocks. You can do all sorts of cool things. You can group these nodes, you can color them, you can rename variables, you can do all sorts of neat stuff. In knowing that all these checks error on failure, we can simplify the graph if you're in a situation like this. So here's the graph that we saw previously, and in this case we just simplified it a little bit. So in a basic block right here, we know that set socket option was being called, and over here host a network and bind was being called. So we could leave it in this big format like this, where all the instructions and you're literally seeing the assembly, or you can do what IDA calls grouping the nodes, and you can group a node by itself, or you can group multiple nodes together. And you just put a short little summary of text in here to display what you want to see. So from the high-level view, this graph has been reduced to just a couple little basic blocks and checks. Now these could actually be grouped even further, and this could just be one block right here that says set up the socket or fail. So we could literally spend all day on IDA, but there's just not enough time. So I'm going to do a quick live demo here that goes over some important things such as the variable renaming, changing your function protocols, comments and grouping, and some other things like that. So real briefly, let me open up IDA. Okay, so this is IDA, and I have the keychecker.exe binary. Excuse me. This is actually the program that you have for your homework, so I won't do too much in it, but I'll give you a little bit of a hint where to start. So now I'm in IDA's graph view. If you open up IDA initially and you're in the text view, hitting the space bar will switch you between the text view and the graph view. Also, if you happen to be in that horrible view, what's it called? Proximity browser. If you happen to be in this proximity browser right here, again, just click in main or whatever function you're interested in and hit the space bar, and you'll be taken into the regular graph view. So we have our basic blocks. We're looking at things. One thing we notice off the bat is that IDA has put some comments, which is really nice. We can see a call to fread is taking place, and IDA knows the prototype to fread, and in fact you can hover over it and see the arguments that it takes, and it even comments in the assembly here which argument is being pushed there at what point in time. So this EAX is your file pointer. Your 10 right here is the size for your read, so on and so forth. And your buffer here comes from ECX. So comments are a nice thing in IDA as well as the function prototypes. Now another thing you can do is you can rename variables. So we know that EAX right here is our file pointer, and EAX came from EBP plus var 1c. So we know that this represents our file pointer, and EBP plus var 1c isn't really helpful, especially if later on the program were to use that. We kind of want to know at a glance that EBP plus var 1c is actually our file pointer. So you can select the variable and right click and rename, or just press the N key. And now let's call that, I don't know, FP for file pointer. And now every time it's referenced, it's simply FP. So you can do this, and again, we could do the same thing right here. This could be our buff we're reading into. And so really quickly, things start to change, and you have meaningful variable names. We can see our buffers being referenced in multiple locations, our file pointers being referenced in multiple locations, and you can quickly clean up the assembly to get much more useful, closer to source information back. So let's continue. Another thing that IDA lets you do is color nodes. So we can see, hey, no bypassing me. We can see some other, and here's, hey, you have the correct key. So different blocks here with different strings in them that are being referenced. So hey, you have the correct key. That's a pretty good block. So if we wanted to see that at a glance, we might color it to a useful color like green. So again, you can accomplish that by, in the top left corner, clicking the Set Node Color button, selecting whatever color you want. That green was pretty bad. Let's try something else. Oh, that was even worse. And it will rename the block, or recolor the block, excuse me. And similarly over here, the hey, no bypassing me, maybe we want to color that red, because that sounds like a failure case right there. Okay, so horrible to read, but they're red and they're green. You know what they are now. So besides being able to operate on single blocks, we can also group blocks. Let's say that close but no cigar, hey, I'm super serious, and hey, no bypassing me. These are all three blocks that represent failure cases. So we want to group them together. We know that if we hit them, the program's pretty much over. So we can, just like any other program, you can control click and select multiple nodes. And then you can go up here and select the, you can right click and do group nodes. So let's just call these fail. And now all those three cases have been grouped into a single one, and you can see this node has multiple entry points from the graph. Now again, you could rename this, and you could change it to something else, and you can also change the color. So we know that this block is actually a collection of three smaller blocks, and they all represent failure cases. So you can click the uncollapse button to expand them and see them in their full form again. But let's keep them collapsed. So similarly, if you realized that this whole group of nodes is just doing some check or performing some simple operation that looks complicated because it's multiple basic blocks, you might select them all. You might decide to right click and group them, and maybe it's check if something happens here. And then you have a much easier graph to look at. So let's see, what else do we want to talk about? We mentioned the comments on the side, but you can also add them yourself. You don't have to rely on IDA to add them. So if we wanted to pretend that this comparison is checking, I don't know, something to 10, you can do the colon, and that will let you enter your comment. My comment. And so you can comment the sides of your basic blocks as you go through it. You can make sense of what's going on, make your own comments, rename your variables, group your nodes, and then color them. So after you spend a little bit of time in any particular graph, you can actually start to get some really good looking code out of it. And a lot of times it's just easier to look at than the source. So let's see. We've already gone over strings and imports from one of the previous exercises, so I'm going to leave that out. The last thing that I'll touch on, there's not something in this particular binary right here that's a good example of it, but renaming your function prototypes. So when I hovered over the fread, you could see it takes 4 arguments, a void pointer, 2 size t's, and a file star. So if this was a, well, let me change fread. Oh wow, it will. So if you want to change a function prototype, you select the function that you're interested in, you press Y. I'm actually not sure how to get to it without pressing Y. I'm sure there's some complicated menu option, but just pressing Y will let you change the function prototype. Now, if this was some unknown function, I obviously wouldn't know what it was. So it would probably just show up as 4 integers by default. And this is what you would see if IDA probably wouldn't even tell you this, to be honest. You would know it was 4 integers, but it wouldn't comment it for you, or sometimes it will, sometimes it won't. But this is what you would get by default. And so by filling these variables in, you're going, well, no, this isn't really an int, this is a void pointer for your destination. And we've already renamed this variable to buff, but if we hadn't, changing that prototype would make this variable name dest. And any other function that called this, IDA is smart enough to connect the local variables to match up with the prototypes. So if a different function called this, it would go ahead and rename that variable to dest as well. So as you rename a couple of functions that are commonly called, the rest of your functions actually get their variable names filled in at the same time. So anyways, that's enough for IDA. That's a fantastic tool, and if you're interested in reverse engineering it, it's one you must be familiar with. So let's see if we can continue this. Okay. So here's your exercise number 3. Can you figure out the correct input to get the key program to print the key? And the executable for this one is numberchecker.exe. So again, this is being recorded, so if you want to do this exercise, just go ahead and pause it right here. I'm going to continue along to the solution. So let's see. Numberchecker.exe. Okay, and here we have number checker open in IDA. So I'm going to use a couple of the features that we learned from IDA to simplify this a little bit. Now, it's not that big, and we can see there's only a couple of comparisons happening. One way branches you to your key is, or the key is, and the other 2 ways look like pretty obvious failure cases. So I'm going to go ahead and group the 2 fail cases together. I'm just going to call them fail. I'm not going to color them because I don't want to see that red. So let's see what's going on first. We are in main. We have our function prototype for main. We're comparing argc to 2. Now, if we were successful, we continue. Otherwise, we jump to one of the fail cases. So right here, I'm going to go ahead and comment and say must pass an argument. Now I said an argument, not 2, because argc's by default is 1 because the first one is the name of the program. So this just means you must pass it a single argument, which would make argc 2. So if we were to pass an argument to this program, we would be successful and fall into this basic branch, or basic block, excuse me. So now we're calling a to I, which is alpha to int, takes a char star, and returns the integer representation of that. Now what's it passing to it? Well, ECX. And where did ECX come from? It's the dereference value of EAX plus 4. And where did that come from? Well, that's argv. So argv, like I said, argv0 is going to be your program name. And if it were to just dereference EAX, that's what you'd be getting. But it's dereferencing EAX plus 4, so it's getting argv1. And that makes sense. And A2I on your program name doesn't make a whole lot of sense. So that's what we have. We're calling A2I on argv1. So we're getting the integer representation of whatever your first argument you passed to this program was. We're adding ESP4 to clean up for the stack that for the argument we just passed on the stack. And then we're putting that return value into this var18. So let's just call this user int. So this is whatever integer the user decided to pass on the command line. And now we're comparing it to 0, and if it was less than or equal to, we jump down to the fail case. So we know our value must be greater than 0, and now we also do another comparison to 3E8. And this brings up another point. 3E8, the H there means hex. That's not very intuitive. But you can right-click this, and you can change the format. So you can see the binary representation, the octal representation, but we just want decimal. So we're comparing it to 1000, and if we are less than, we'll take the green branch, which brings us over to here. If we were not, then we would fail again. So must be less than 1000. So now let's go ahead and group these nodes. And this is a little bit overkill, but just for the sake of doing it. So we're getting some variable is equal to A2I of argv1, and we know that we must be greater than 0 and must be less than 1000. So that's basically what's going on here. And if at any point in time we fail any of those checks, then we would come over here to the fail case. So there's a little bit of fancy math in here with the compiler optimizing some stuff out, and you can look up some of these instructions later. But what's going on is we're getting the user int, we're putting an EAX, converting a double to a quad, so converting a D word, a D word to a quad word. So we're converting 4 bytes to 8 bytes. We're moving into ECX2F, which again, not very helpful, so let's make that a 47. And then we're doing a division. So, and then it tests EDX. Test is simply an AND operation, so this is basically saying AND EDX with EDX, and then you set the appropriate flag. So if the result was 0, the 0 flag would be set. And in this case, we're doing the test EDX with EDX. And in a division operation, the remainder is going to be placed in the EDX register. So by testing it and jumping if we were not 0, this is essentially doing a modulus. This is really doing modulus 47, and if the remainder was not 0, jump to the fail case, or the end, XOR EAX with EAX and return. So we know that the remainder should be 0 because we want to continue this. So it's a little bit of tricky math going on here, but it's really just a modulus operation. So I'm going to go ahead and group this node right here with itself and just say must be mod 47. And the exact same thing is happening here. The user input is being divided by 15. The remainder, which is in EDX, is being checked for equality to 0. So I'm going to go ahead and group this as well. Must be mod 15. And if we satisfy both these cases, we fall into this block. Now, this is sort of a telltale sign if you were to see this on sort of a CTF. This is the programmer trying to hide his flag for you. And the only reason I did this is so when you strings the binary, you don't get the flag just popping out. Because these single bytes are not going to be stored in the data section. If I just had a single string saying like, you know, A, B, C, D, 1, 2, 3, that would show up in your string section, and that's not much fun. So again, these are ASCII representations in hex, and these are really easy to pick out after you've done this for a while. So let's go ahead and change this to, we're going to right click that, and the R option will set it to the ASCII value. So I'm going to go ahead and select these and press R a couple times, or just once, and change them into their actual ASCII values. Now, you can see this is definitely a string. However, it's not a human recognizable one at first glance, and that's because they're being moved into different locations within this variable. This is actually a buffer on the stack. This is just a character buffer of size, 10 or 15 or whatever this is, and the different slots are being moved into them. So it's not just being moved into location 0, location 1, location 2. Otherwise, you'd be able to read this just fine. But, so we know we must pass in an argument. It's converted to an integer. We have to satisfy these two checks. We have to satisfy these other two modulus checks. And if so, we would fall into this basic block right here, which is basically our success case. So let's go ahead and color that appropriately. And that's the end of the program. Like number checker, we see oops, try again. And if we were to pass it a value, we would get a different code path to be executed. And you could follow this through, and this was the case we fell through right here, was just the XOR EX with the AX. So let's see. And we know our value must be between 0 and 1000. So let's just iterate over that range. Oh, and there it was right there. So we know the key is 705, and then you get, or the correct value that satisfies those two modulus operations is 705, and we get our message, great job, the key is reversing rocks. So with a little bit of IDA, you can make it a binary much simpler to analyze and quickly figure out where it is you need to be attacking the application. So let's continue back with the presentation. So everything we've done so far has been static analysis. We're going to spend a little bit of time going through dynamic analysis now and do some debugging. There are a couple things to keep in mind. Well, there's a couple things to note first. A good debugger is going to have several features, and then these are usually pretty common features for any good debugger. You're going to be able to set your breakpoints, you can step into or over functions, you can show your loaded modules, you can search memory, and a myriad of other things. Now, WinDebug, OLLI, Immunity, IDA, GDB, most of these are going to fall under the good debugger category. One quick note to keep in mind, you do control everything. If you want to skip over an instruction or a function call, do it. If you want to bypass the authentication method or make it return true, that's something you can totally do. You can change the contents of registers, you can change the contents of memory anywhere in the program you want. You can even patch a program and save it, and then you have a new executable. A lot of people will be very timid in their first couple debugging sessions, and they won't want to change things, and they're worried about messing up the program. Don't worry about it. If the program crashes, just run it again, hit your breakpoint, and then make your change and continue on. So feel free to play with these programs in any way you see fit. Now, I'm going to go through IDA's debugger briefly. And a lot of these things carry over to OLLI and Immunity, in particular the hotkeys. So this is the debugging, this is a screenshot of the debugging output within IDA. F2 will set your breakpoint, and currently it's set on this call interlocked compare exchange function call. And F2 again translates over to OLLI and Immunity, and then both of these set breakpoints with that. And at the time that breakpoint has been hit during debugging, there are multiple things that you'll see on your screen. One, you'll see the disassembly that we've been seeing the whole time, but some other windows will pop up. One of these will be your registers window, which will have your basic registers in them. We'll show you the contents of them, and if they happen to point somewhere, it'll even comment on the side what that is. You'll also see the stack, and on the stack, the left-hand column here is going to be your address within memory. So your stack pointer right now is pointing, has the value 46FA40. and the memory at that address is this content right here. And you can see these match up. So we're on this call instruction. So the last instruction to be executed will push EDI. If we look at push EDI, the contents of EDI are 13033B0, and on the top of the stack, that's the data that we see there. So all these windows match up, and looking at things different ways can certainly be helpful. Now, the function call that we're broken on right now is interlocked compare exchange. And if you look at the prototype on MSDN for this, it takes a long pointer to a long LP, yeah, it takes a pointer to a long the destination, takes a long exchange and a long comparand. That's weird. So, knowing the data types of function parameters and function prototypes is extraordinarily helpful. If you had no idea what this function call was, or maybe you just knew what this function call was, but what nothing else in that function was, then you can break on the function call. You can figure out the function prototype, usually by looking it up, in particular if it's a library call, and then you can work backwards. So if you know that, EDI in this case represents your comparand, then you could go back up, figure out where it came from, and in IDA rename your variable to comparand. And you could change, maybe if that was an argument to the current function, maybe you can change the function prototype for that. And you can do this with multiple variables, so you can work backwards, rename them, set your data types, fill in function prototypes, and suddenly just by using library calls, you can sort of fill in your program and see what's actually happening. So again, this is another exercise. We'll be using numberchecker.exe again for this. And the question this time is, can you bypass the key check entirely? So in a lot of CTFs, when you see a function like that, where there's a bunch of bytes being moved into some sort of buffer and then printing a string or printing a value, that's sort of a big red flag. And usually you can get a really quick low point problem this way, like a 100-point problem. But try to just skip everything and just get it to print your success case and print your flag right away. So again, if you're watching it, just pause the program, or pause the presentation rather, and I'm going to go ahead and continue along to the solution. Okay, so the solution here, there's multiple ways you can do it. One is just set a breakpoint right in the very beginning of your function. Now, you'll notice I didn't do it on the very first instruction, push EDP. I actually did it right after the prologue. So the prologue sets up our stack frame, remember. It creates some local room, creates some room for local variables, and then I broke right here on the instruction right after the prologue, just so I can continue the program at the end, and the epilogue will work cleanly and the program will exit nicely. Now, when the program is stopped, where is it that we want to go? Well, we figured out this basic block was where our key was being printed, so we can just literally right-click on this basic block and say set IP, set the instruction pointer, and that's the equivalent of EIP. And when we do that, literally, you can just press go from then on. I'm not going to do it because it's very simple. And you can just hit go, and your output's going to be printed to the screen, and you've successfully, well shoot, I'll go ahead and show it. And you've successfully printed your key. So, real quickly, I'll do that. This is where we want to go. This is the beginning of the program. Now, if you see no debugger selected up here in IDA, just do your local Win32 debugger. I'm going to move to the very beginning of this function right after the prologue. I'm going to set my breakpoint and hit play. Yes, you are going to get warned that you're about to run a binary on your computer. Make sure you press yes because it's my binary. Okay, now we're in the flat text view in IDA. This isn't where we want to be. We're going to hit spacebar, and now we're back in the graph view. This is much more familiar. And you can see this is where we are, the line that's highlighted. We have our stack view down here. We have the hex view over there. Not super helpful for what we're trying to do right now, but let's go ahead and move things around a little bit. And now we've got a little better output here. Our registers, our stack, and disassembly. So this is fairly clean. In IDA, your hotkeys, F9 is going to continue the whole thing. F7 steps into and F8 steps over. Now what that means is if you run a call instruction and you were to step into it, you would begin tracing into that function and you would follow that function all the way through. If you do F8, you're just going to step over it and pretty much ignore the call. It's going to happen, but you're not going to see it. So we're broke right here at the beginning of the function. let's go ahead and just move to the beginning of this basic block because this is what we're interested in. I'm going to right click, set IP, and now I'm right here. So I'm going to go ahead and F8 or F7, whatever makes you happy. Now you are going to want to F8 to step over the printf. And right here, if I hover over the console, nothing's on it yet. Nothing's happened. So let me go ahead and step over this call to printf. And let's check it again. We can see great job has been printed. Okay, so this is being executed. We're going the right way. Let's go a little bit further. The key is, and let's execute that call to printf. And here we can see the key is reversing rocks. So if you would have hit F9 and just finished the program, then it probably would have just closed the terminal for you and you wouldn't have been able to see the output. So you may want to single step it or just set your breakpoint right there and just jump right, or you can press continue and stop right after the printf. So let's continue. Okay, so most of the Windows debuggers, like I've mentioned, are similar. You have the same windows that you can see pretty easily. You have very similar hotkeys. The exception is, and this isn't a Windows debugger, but the exception is GDB. Oh, excuse me, I said that wrong. The exception is WinDebug. WinDebug is similar to GDB. I don't quite agree with that statement anymore in my presentation, but it's more like GDB in the sense that it's more command-oriented. So from WinDebug, you'll be executing more commands and you'll be doing stuff more manually, where in something like Ollie or Immunity, you have more of a graphical interface to work with. While you do have a GUI right off the bat in Ollie and Immunity, I highly recommend WinDebug. It is by far the most powerful Windows debugger, and you can easily get a GUI for it by playing around with some of your windows. But anyways, GDB is where things get a little bit different. So GDB is going to be your Linux debugger, and it has some pretty funky syntax. So we're going to go over GDB briefly. We'll do a quick exercise with GDB, and then we'll wrap up. So first things first, you got to launch the program using GDB, or attached to it, whichever way. So GDB and then /myprogram is going to launch GDB and start debugging the program. Now if you want to pass arguments to the program, you can pass it the --args flag, GDB --args myprogram, argument 1, argument 2. So within the program, we'll run the program, and if you want to pass arguments from inside GDB instead of on the command line here, you can do run and pass it argument 1, argument 2, and so on and so forth. Now, a neat trick is you can still do your little shell extension right here, basically, where you run another operation within another shell, and the result is placed here. So within GDB, if you wanted to pass, say, 1,000 A's to the program, you could say run, do your $ parentheses, the command you want executed, and then closing parentheses. And you could do this on the shell. If you were to echo, instead of run right here, it would echo 1,000 A's because this gets executed first. The result is replaced in line right here, and then the outside function is run. So this is just normal shell functionality, but it's neat that you can do it within GDB. So here's a little screenshot of debugging the Linux debug example. So I've ran GDB-Q, Linux debug example, and the -Q flag means quietly. Normally you get a banner with GDB that prints a bunch of stuff on the screen, and -Q just says be quiet. And now that we're debugging the program, and we launched it, and it's not running, it's broken at main by default. So nothing's been executed, and we're just sitting at main. So I'm going to go ahead and press run, or type run here. And then we see this message from the screen, missing something, and the program exits. So we're clearly missing something here. We need a little bit more information. I would just open it in IDA, but we're trying to learn GDB. So let's use GDB to figure out a little bit more what's going on here and why our program just exited telling us we're missing something. So again, AT&T is known to be better. Wow, I said that wrong again. Intel is known to be better than AT&T. So we can set the disassembly flavor to Intel, and that's the first command here. That's going to give us Intel syntax rather than AT&T syntax. The disassemble function, I think you can even shorthand it with just dis. Will disassemble whatever function you pass it. So in this case, I've opened up the program, haven't done anything but open it up. I set the disassembly flavor to Intel, and now I'm going to say disassemble main. And now we get this nice, what should be familiar, black screen, white text, big dump of text. And so this is what I was showing you in some of the previous examples, was GDB output. So we see our familiar prologue, we're making room on the stack, there's some compares being performed, and then some jumps being taken. So this is probably interesting, but I think we get there in a second. So let's use some more GDB to figure it out exactly, rather than just looking at the disassembly, because if we're going to do that, we should be in IDA. So let's go ahead and break on main. To set a breakpoint, you can either break on a function call, in this case break on main, or if you want to break on a specific address, you break star the address. Now if you ever want to see what those breakpoints you've set are, you can do info breakpoints. You can do delete breakpoint followed by a number to delete a specific breakpoint in your output list, or delete breakpoints, plural, to delete all your breakpoints. So in this case, we're going to break on main, and we're going to run the program, and we're actually breaking at the call to main here. Now stuff does happen before main, the program sets up, and some behind the scenes operations take place. But now we're actually breaking at main while running the program. So your basic instructions are SI and NI. SI is your step instruction, which will go into, and it's different than all the Windows debuggers, and it's very annoying, but step actually steps into functions, and next steps over. So I always have to write them down on the whiteboard because I forget, because GDB sucks. But SI and NI are your main moving around operations within GDB. And here you can see some SI and NI operations, and the addresses are changing because you're slowly stepping through the program here. But this didn't really help us very much. We can single step through the program, we can step over function calls, but again we just hit the end here and it says missing something. So we need a little bit more information. So now we can disassemble, we can set breakpoints, we can step through the program, but we still need to be able to see the contents of registers, we need to be able to see the contents of memory, and if we so choose, we need to be able to modify registers and memory. Now this is where GDB gets a little odd. The syntax here to analyze memory is a little bit funny. So it's not that bad once you remember it, but it's a little bit funny off the bat. So the syntax here is X, I guess to I don't know. Anyways, it's X slash the number of units, F is sort of the format or the type, and U is the unit itself. So it seems a little convoluted, but look at this and we'll make a little bit more example. So we want to examine 5 instructions, I for instructions, and where at EIP. And registers in GDB are referenced, are prefixed with a $sign. Okay, so let's look at the next one. We want to examine 4 hex words at ESP. Okay, that makes sense again. Now let's skip down here to, we want to examine 5 bytes at ECX. So it's not too bad, it's just a little odd the first time you see it. And here again is how you examine a string. It's simply X and then S for string and the address. Examine the string at this location. Registers, you can see with the info register command. That will show you all your registers, or you can shorthand it with IR. And if you just want to see specific registers and then all of them, it's just IR and then a list of register names. So a little odd, but not too bad. What do you want to do? You want to examine how many, 4, what types, and what words or what sizes, at what location. So it's all the same, it just takes a little bit to remember it. Okay, so we have a big blob of text here, and this is me stepping through the program with GDB and analyzing different things at different points in time. So the first thing that happens is we're in the program, we hit run, and we've hit our breakpoint in main. So I guess I probably missed a command where I set breakpoint on main. Now, when we break, we're not seeing any instructions, so we need a little bit of context here. Let's see exactly where we are, what's about to get executed. So let's check out EIP. So in this case, we're going to do examine 5 instructions at EIP. And we can see we get a little bit of the prologue there, a little bit of the subtract ESP, and then a comparison takes place. So let's continue until we hit an interesting function, or an interesting instruction, excuse me. So we're going to step a couple times, and now we're actually on this comparison. We're comparing EBP plus 8, the dereference value of EBP plus 8, to 3. So let's see what's in that location. So here we want to examine the hex word at EBP plus 8. And this is the address at BFFFFCD0, and the value in that memory address is 1. Well, 1 does not equal 3, so we're not going to jump on equal. And then, which means we're not going to take this jump, we're going to move this address into ESP, and then call puts. And puts is just like printf, it's going to put a string to the screen. So let's see exactly what is in that address when we're on this instruction. So we examine the string at this address, and it says missing something. So this should be familiar. This is what just got executed in the last previous iterations. So we know now that we're not satisfying this comparison. 1 does not equal 3, and puts is called to the string and the program exits. So what is that value 1 at EBP plus 8, and how do we influence that? Well, remember the function prototype for main is int argc and then char star star argv. So EBP plus 8 is where your first argument is, which is argc, and we were not passing that function, we're not passing that program any arguments rather, so it makes sense that it only has 1, it just has the program name in argv0, so argc is 1. So this is comparing the number of arguments to 3, and we did not satisfy that, and hence the error message or the print statement that we got. So if we were to pass 2 more arguments, and remember that would be 3 total, we would see that it does in fact satisfy the first compare instruction. So here's the previous iteration, / Linux debug example, and missing something is printed to the screen. Now, if we run this again, passing in 2 arguments, some A's and some B's, that message is not printed to the screen. So a new code path was taken, and we could analyze that to figure out what happens. So that's going to be your exercise 5. Spend a couple minutes, try to figure out the correct input. It's going to cause your program to print the congrats you did it message. So feel free to use a combination of IDA and GDB, and go ahead and pause the presentation if you want to do that. I'm going to go ahead and go through the example. So here we have an IDA, the binary, and I'm much more comfortable in IDA than GDB, so this is where I'm going to do most of my work. And let's see. We can see arg0, which we know the function prototype for main, even though IDA didn't put it in here. So let's go ahead and fix that. Press Y to change the function prototype. Make that argv. Actually, you should make that argv and this argc. And we can see by changing the function prototype and giving it a name, I'd actually change the name within the program itself. So that's helpful. So we're comparing the number of arguments to 3. So must pass 2 arguments. And let's continue down. So it pulls out argv. It adds 4 to it, so it's pointing to argv1, and then calls alpha to int on it again. So this again is alpha to int of argv1. And the return value is in EAX, and the return value is then placed in ESP plus 4C. Unfortunately, it didn't recognize this as a local variable, and we could go up into the stack and then we could change that. But it's such a small program, I'm just going to make note that ESP plus 4C is the value that we pass it. So it does a comparison and checks it against 36 hex, which what is that in decimal? 54. And if it was below or equal, we're good, and we take this green case, we satisfy that check. But if we were greater than, well, below or equal is here, so if we were greater than 54, we fail. So we know our input must be less than or equal to 54. Okay, so we have our two fail cases. I'm going to right click and group these two nodes, and I'm going to say fail. Okay, that changed things up a little bit. So we passed two arguments. The first one is converted to an integer and must be less than or equal to 54. Now we see a string copy operation happening, and let's use IDA's comments to figure out what's going on. So the destination is coming from EAX, and LEA is loading the effective address of ESP plus 26. So ESP plus 26 is the string copy, and ESP is pointing to your local stack frame. So this is just a local buffer within the function, and you can figure out the exact location of it with a little bit of math that I'm not going to do. So, and the source, let's see where the source is coming from. At ESP plus 4, it's coming from EAX, and EAX is coming from argv, but this time instead of plus 4 and then being dereferenced, it's plus 8. So this is argv2. So let's go ahead and fill in what we know here. We know we have stir copy into some local buff, argv2, and we don't know the size yet. Let's look at the size. Okay, n is the size. It was nice enough to comment for us. It came from EDX, and that came from ESP plus 4c. Well, ESP plus 4c was the value that we passed on the command line. So the string copy that's happening right here is basically this. And in fact, since that's a one-liner, and that's pretty short, let's go ahead and group this node, take away some of that text, and this is what's going on here. Now, oh, actually, let me expand that because there's a little bit more at the bottom. Okay, so the string copy happens, and then we compare the value at ESP plus 4c to ABCD, or let's go ahead and leave that in the hex form, 41, 42, 43, 44. And if it was not equal, then we take this case over here and we return 0. If it was equal, then we jump over here to the congrats you did it. Now, that's interesting. We're checking to see that the value we passed it for the length is 41, 42, 43, 44. But up here we check that the length must be less than or equal to 54. I mean, this is not going to change. It must be less than or equal to 54. So how can we pass it 41, 42, 43, 44? Well, there's a little bit of funny stuff going on here. Let me see. Clear this out. And here's our Linux debug example. We don't pass it anything. We get our familiar missing something. And if we pass it a couple A's and a couple B's, then we hit the case where it just returns 0. So now we know we can't pass it. Let's see. What is... That's the decimal value of the hex 41, 42, 43, 44. And then we're going to pass it some string that's going to be string copied. And it says closer. So we tried to just go ahead and set the value. We pass it to 41, 42, 43, 44, but we failed this check right here, and we can verify that either in GDB, or you can see the only way you hit this closer output is by failing this comparison and you're being greater than 54. So that's not going to work. Now, I'm not going to do the math, but if you spend a couple minutes and look at this, you realize what's actually going on is a little buffer overflow. So we have our ESP up here somewhere. We have some space on the stack, and then we have our buffer that starts here. and our buffer continues on for 50 bytes. And then down here we have the size. And this is the alpha to int of argv1. So what happens, buffer is only 50 bytes long. When we pass it 54, which is a valid input size, we fill up all 50 bytes of buffer, and then 4 bytes in overwrite size. So by passing an input of 54, and then a bunch of junk, 50 bytes of junk, and then our ABCD, which is our 41, 42, 43, 44, we're actually passing the length check, and then writing down buffer a bunch of junk, and then at the very end here, the last 4 bytes actually overwrite size on the stack. So it's a little mini buffer overflow, and I encourage you to spend some time with GDB, set a breakpoint on the string copy, right, and analyze the stack right before and right after. Alternatively, you could look at IDA and figure out the exact location. So we know the destination is at ESP plus 26. We know that we can only copy 50 bytes. So ESP plus 76, well, that's funny, that's 50. So 5 more would actually overwrite that location. So whatever you feel more comfortable with, this is a tiny little buffer overflow happening right here. Let's see, we can probably do this really quick. So A times 50 plus ABCD. Oh, help if I put the 54. Oh. There we go. It's backwards because it's hex. And congrats, you did it. So this was a tiny little buffer overflow, and you actually overwrite a local variable on the stack. So again, look at that in Linux or GDB or IDA. And let's continue. Oops. So static versus dynamic, everyone has their own preferences. Some people will just jump right in and start debugging. Some people will just stare at IDA for a long time. Undoubtedly, the combination of the two is ultimately going to give you the best results. So being comfortable statically and dynamically analyzing binaries is very important. There's also some cool scripting features. So IDA, WinDbg, Immunity, and GDB all have scripting. In fact, they all use Python. And that except WinDbg note right there is no longer true. There is a WinDbg Python API available now. So a lot of automated things can be done. You can automate unpackers, you can automate some other cool stuff. So the last exercise, which actually is going to be the homework this time around, is keychecker.exe, and I opened it up briefly in one of the previous exercises and renamed some variables and stuff like that. And the goal with keychecker.exe is to get it to print the the congratulations you have solved it message. So you'll have to provide it with something to satisfy the checking that it's going to do. For those interested, there is a pretty cool CrackMe, this woodman.com, this link right here. It's a little bit tricky, but that's okay, and there are some tutorials online. In fact, I have one on that is super small. Let's see if we can change that a little bit. So on csg.utdallas.edu, I actually have I think it's like 9 or 12 pages or something like that. It's a little write-up step by step, walking through the entire CrackMe with IDA and renaming your functions and changing your prototypes and filling in your variables and then reversing a little bit further. And it steps you through the whole process of this CrackMe. So for those interested in this, that's a fun one to check out. It doesn't take too long. And one quick note before we finish up, what about bytecode? So everything we focused on has been compiled binary applications. What about .NET? What about Java and Python and other languages that produce bytecode? Well, I kid you not, just download a disassembler. You can download a .NET disassembler, you can download a Java disassembler, and you get almost complete source code back. In most cases, it will compile just fine. You're going to lose pieces of information like variable names, but you get back pretty much source code. It's crazy. I mean, you just run it through a program and you're done. It really is that easy. And there are some obfuscators out there, but there are some deobfuscators. It's like everything else. So that's it, folks. Hopefully you feel comfortable. If I were to hand you a binary, you could open it up. You can look around at the imports and the strings and sort of get an overall feel for what the binary is doing just at a high level view. And then when you actually jump into the program, you can do some disassembly, rename some variables, and figure out exactly what's happening within the disassembly and convert it back to source code where you need to. It's not always needed. In fact, most of the times not, but certain places it's helpful. And then for those gaps where that's just too much to look at statically, or you may prefer dynamically to begin with, you can fill in the gaps with a debugger and manipulate it and make changes to the program during execution. A couple of resources for those interested. Reversing the Secrets of Reverse Engineering. This is a fantastic book. I highly, highly recommend it. The IDA Pro book is great as well. IDA is the industry standard for reversing, so if you want to get more familiar with IDA in particular, it's a fantastic book. The Art of Exploitation is, I believe, you're reading for the course, so that one you're probably already familiar with. There are some great challenges, smash the stack, some crack me's you can get connected to. Some useful links. I got to plug the CSG, obviously. Anyone's welcome to hop in IRC, by the way. And you've already looked at CFF Explorer. Hexrays is cool, but not for probably not for a student budget. And Immunity. And I don't know why I would link Immunity. I would get rid of that and say use WinDebug. But that's it, folks. I appreciate the time and best of luck.